Hello and welcome to this lecture in the course for Secure Systems Engineering. So, in these sequence of lectures, we have been looking at trusted execution environments. In this lecture, we will be looking at the ARM TrustZone. So, a lot of this information that we will be covering in this lecture can be obtained from this link, which is about the TrustZone architecture. Before we go into the ARM TrustZone, we will take a look at what the system on chip means. So, a typical system on chip would look like something like this. It would have various components corresponding to the various different functionality. So, you would have, for example, the main processor. You have a lot of different modems, GSM 3G modem. So, this is shown for a typical say a mobile application, and you would also see various other components such as ADC DAC, timers and so on. So, all of these things would be present in a single chip. Now, the advantage of having such a system on chip architecture is that the size of your complete design is reduced considerably. So, for example, if you take the case of a mobile phone and you actually open up your mobile phone, you would see that there are very few ICs present on it, and the reason being is that each of these ICs have a lot of different functionality. So, in prior years, prior to the system on chip type of architecture, you would have a different IC present for each of these modules, and therefore, the size of your entire design would be quite large, right. Now, with the advent of the system on chip and a lot of all of these components put into a single chip, the size has reduced considerably, and this has actually caused a large number of different opportunities. For example, the size of mobile phones etc. have shrunk thanks to this particular technology. So, now we will go into a bit more detail about the ARM TrustZone. So, the ARM TrustZone essentially creates two partitions. It creates a normal world and a secure world. So, the figure looks something like this. So, in the normal world is where you would have your typical operating system like your Android operating system or iOS, and you would be running your typical tasks like your WhatsApp or anything else. So, all of them run in this normal world. Now, you would have a secure world as well, which would run your sensitive tasks. So, all your sensitive operations such as, for example, encryption or entering sensitive data like passwords or OTP numbers would be handled by the secure world. So, for example, you could consider this, right. So, you would have normal world applications, and whenever, for example, you require to do some sensitive operation, the processor shifts to the secure world. You enter your password which gets authenticated, or you enter your OTP or do an encryption which further gets verified, and then once it is verified, you switch back to the normal world. So, ARM provides this particular environment and provides and manages the switching between normal world and secure world. Now, the hardware is built in such a way that the normal world applications will not be able to access or is totally isolated from the secure world applications, and therefore, all the sensitive information and secure computations which is done in the secure world is completely isolated and completely independent of the normal world operations. So, thus any software vulnerability or any malicious code, any malware present in the normal world cannot steal information or cannot affect the secure world operations. So, just to take an example of how it would typically look like. So, let us say we have an Armory application as shown over here. So, the Armory application runs in the normal world. So, we call the operating system present in the normal world as the rich OS. So, your typical Android operating system or the iOS operating system is the rich OS. So, we call this the rich OS because it is filled with various features, and most of your applications would be running in this rich OS and making use of the various features that are supported by that particular operating system. So, let us say we have this Armory application running from our rich OS, and there is one button over here which says that the user has to enter a PIN. So, when this button is pressed, there is a switch from the rich OS, that is from the normal world to the secure world, and in such a case, and there would be a execution in the trusted environment. So, in this particular mode or the secure world, it would pop up a window like this and request the user to enter a PIN. So, all of these transactions in the secure world is completely isolated or completely done securely and not accessible from any of the applications present in the normal world. Even the Android or iOS rich OS running from your normal world would not be able to have access to the PIN which is entered by the user. So, once the PIN is entered through the display driver and the input driver, there would be a trusted user interface which actually reads these information and passed on to the trusted application, which then authenticates the PIN using keys which are stored in the trusted environment. If the authentication is right, then an OK message is sent back to the normal world application, that is the Armory application, and the user of this application would then continue to use this application. So, what you see over here is that because of the trust zone which is supported by the ARM, all the activities, all the keys, all the authentication which is done in this trusted environment or in the secure world is completely isolated from the user world applications. So, the keys and so on are secure in spite of any malicious code that is present in the normal world system. So, even if your Android or iOS is compromised, still the keys stored in the trusted environment is still safe and secure. So, we will look a little bit about how ARM actually manages these to have two environments, the secure and the normal world environment within the same processor. So, essentially these two environments work in a time slice manner. So, there is a switch from the secure world to the normal world and vice versa. Further, there is a new mode of operation that has been introduced known as monitor mode, which essentially gets invoked whenever there is a switch from one mode to another on return. So, there are two ways in which these mode switching is triggered by. First way is by software, by an instruction known as the secure monitoring call or the SMC instruction. Second, you could also have hardware interrupts or exceptions which occur, and this could also lead to a switching of modes from normal to secure. Now, the monitor mode plays a crucial role during this mode switching. First, what it does is that it saves the state of the current world, that is either normal world or the secure world, and restores the state of the world that is switched to. So, the restoration is done when there is a return from an exception. So, for example, whenever there is let us say that an interrupt occurs, the first thing that gets executed is code present in the monitor mode. So, the monitor mode would then identify the interrupt that has occurred. It would save the context of the current world, that is, if an application is running in the normal world, the registers corresponding to that particular application is saved in the monitor mode, and then there is a context switch to the secure world, and the interrupt routine corresponding to that particular interrupt is then executed. After that interrupt service routine is executed and the interrupt gets handled, there is a return from exception instruction that gets executed. Now, this would result in the monitor mode getting executed again, and then the monitor would restore the state of the application that is executing. Now, in order to keep track of the mode of operation, the ARM has a particular bit known as the NS bit. So, the NS bit present in the configuration register indicates whether it is a normal world or the operating world that is currently being executed. So, for instance, if the NS bit is equal to 1, it indicates that the processor is in the normal world. If the NS bit is set to 0, that would indicate a secure world operation. Now, the NS bit is present in a configuration register present in the main processor, and based on the value of the NS bit, the processor over here, the Cortex A8, works in either the normal mode or the secure mode. Similarly, the cache present in the processor is also able to distinguish between memory accesses which are for the normal world and the secure world. But there is a lot more things that happen when there is this mode switch. One important thing for us is that this NS bit also extends outside this processor component. So, for example, over here we show that the red line indicates that the mode of operation is also transferred to other components present in the system on chip. So, thus other components will also be able to distinguish between a secure world operation and a normal world operation. So, for example, an important thing for us, as we will see later, is that the memory controller present in the system on chip would be able to distinguish between memory access which is made to a normal world operation and a memory access made to a secure world operation. Now, so we look at a little more detail about the memory management present with TrustZone. As we have seen that the CPU core, that is a Cortex A8, will be switching from the secure world and the normal world, and the NS bit present in the CPU configuration register would identify which world is executed. Now, every time there is a load or store instruction from one of these cores, either the secure world or the normal world mode of operation. So, whenever there is an instruction from one of these worlds, either the secure or the normal world, what is done is that there is a virtual address put out on the bus. So, this virtual address goes into the memory management unit. So, a typical 32-bit ARM core would put out a 32-bit virtual address on this particular bus. Now, with TrustZone enabled processors, an additional bit known as the NSTID bit, this is a 33rd bit, would be also put out on the bus. So, this particular bit would identify the current state of the processor. It would have a value of 0 to indicate that the load or store operation or the instruction that is requested is from the secure world. If it is 1, that bit would indicate that the load or store or instruction fetch would be from a normal world operation. If the NSTID bit is set to 1, then the NS bit is forced to 1. Now, thus, because of this additional NSTID bit which is sent to the MMU would be able to identify or distinguish between secure world load or store request and a normal world load or store request. So, based on this NSTID bit, the MMU would be able to select page tables or use page tables which are meant for the secure world or the normal world. Okay. Now, the page tables convert the virtual address to corresponding physical address, and each of these page tables would thus be able to point to pages which correspond to secure world pages or the normal world pages. So, for example, if there is a say a load or store request to a particular virtual address, the NSTID bit is set to 1, which would indicate that it is a normal world memory request. What the MMU would do is that it would use the normal world page tables. So, the virtual address would then get translated to the corresponding physical address, and therefore, the mapping is done in such a way that it is only the normal world pages which can be accessed. Now, if this particular virtual address falls in one of these normal world pages in the RAM, then the load or store will be successful. On the other hand, if a virtual address is put out on a bus which actually corresponds to a secure world page, then there would be a trap and the operation would not be permitted. Now, the MMU, as we know, also comprises of a TLB, which is the translation look aside buffer. Now, in an ARM core which has TrustZone enabled in it, the TLB is modified slightly. Now, as we know, a typical memory management unit also has a TLB present in it. The TLB, which stands for the translation look aside buffer, has a mapping between the virtual address and the corresponding physical address. So, this mapping will ensure that once a virtual address is mapped to its corresponding physical address using the page tables that are present, that mapping from virtual address to physical address is stored in the TLB. So, the TLB would be a fully associative cache, and it is expected that due to the locality of the execution and memory accesses, you are quite likely to find the mapping of virtual to physical address present in the TLB, and a lot of overheads will therefore be reduced. Now, in an ARM processor which is enabled with the TrustZone, the TLB is modified a bit. Now, each entry of the TLB not only comprises of the virtual address and the corresponding physical address, but also has details about the NSTID bit corresponding to the virtual address and the NS bit corresponding to the physical address. So, in other words, it will identify whether the virtual address was made with respect to a normal world operation or the secure world operation. Further, it also has information to say whether the physical address corresponds to a page which is secure or in the normal world. So, based on this TLB which is stored in TrustZone enabled ARM systems, the MMU would be able to use the TLB to say permit a secure world page table to access secure pages as well as normal world pages. By having this particular TLB, the MMU would be able to use the TLB to allow secure world virtual address. The MMU would be able to use the TLB to permit a secure world page tables to access a normal world page. On the other hand, it can also prevent a normal world page table from accessing a secure world page. Now, in addition to the MMU, the cache memory present in TrustZone enabled ARM processors is also modified. Both secure world as well as normal world memory requests are stored together in the same cache. However, there is an additional bit known as the NS bit which is stored in the tag. However, the tag is modified so that each tag also comprises of the NS bit. Thus, based on the tag and the NS bit present, a memory request can be identified whether the corresponding cache line corresponds to a secure world cache line or a normal world cache line. Now, in order to make these schemes to work, the memory management unit in TrustZone enabled ARM processors is designed in a special way. So, for example, there are two virtual memory management units that are present. In addition to the memory management unit which we have seen, the NS bit which determines whether the processor is running in secure world or normal world can be actually sent to all other components present in the system. Thus, one would be able to configure a particular component in the system to work only from a particular mode. For example, over here what we see is that the GSM modem, 3G modem and the media system is configured differently. So, the GSM modem is configured so that it works only when the main processor is running in the secure world. On the other hand, the 3G modem is configured to work both from the secure world as well as the normal world. Putting this in other words, when the main processor is running in the normal world, it will not be able to access the GSM modem. Thus, applications running in the normal world would not be able to even see that the GSM modem is present in the SoC, and no communication to the GSM modem is possible. On the other hand, when the main processor is in the secure world or configured for the secure world, then the GSM modem, the 3G modem and all other devices would become accessible. So, this technique is essentially useful, for example, where we were able to configure say the keypad to only work in the secure world. So, this would permit that whenever we enter passwords or pins or anything else. So, these passwords and pins are only accessible through a keypad which is enabled during the secure world of operation, and thus it is also secure from any kind of snooping attacks. So, interrupts are a critical aspect with respect to TrustZone. So, as we have seen, there is a monitor mode present over here. So, the monitor is part of the secure world, and what we see is that whenever an interrupt comes, so it is first channeled to the monitor mode. The monitor mode will save the context of the current executing environment and then decide whether that interrupt should be serviced by a normal world application or a secure world application. So, based on how these various interrupts are configured, this interrupt request would be either channeled to the normal world interrupt service routine or the secure world interrupt service routine. So, each of these worlds would have its own interrupt vector routine, which would then look up the corresponding interrupt request, determine where the interrupt service routine is present, and then execute that corresponding interrupt service routine. So, for example, your privilege code over here could be your Android OS. So, let us say for example that a network interrupt occurs and network interrupts are configured to be handled by the normal world. So, therefore, the monitor would channel the network interrupt to your privilege code, which essentially could be your Android operating system. Your Android OS would then look up the normal world interrupt vector table, identify the interrupt service routine corresponding to the network interrupt, and then execute that corresponding service routine. On the other hand, if the interrupt happened to be a secure world interrupt, the monitor would then channel that secure world interrupt, which would then look at a secure world interrupt vector table and identify the corresponding location for that interrupt service routine. We now look at how a typical secure world software looks like. A typical secure world software would have implementations of very minimalistic implementations of synchronous code libraries. So, typically we would have a operating system present in the secure world. So, these are specialized operating systems which have very minimal functionality. So, operating systems such as Qualcomm's QSEE, Trustonics, Queenie, Samsung, Knox, Genode, etc. are secure world operating systems. So, these operating systems are tightly coupled to the corresponding rich operating systems, so that a priority of a task in the rich OS can get mapped to a corresponding priority in the secure OS. So, advantages of having a full OS is that it will have complete. One thing that is critical with respect to TrustZone is something known as secure boot. The reason why we require some secure boot is the following. So, let us say that we are having an application that uses the secure world. So, as we know that the application would be stored in the flash, and what could possibly happen is that an attacker could modify the flash contents and therefore could modify the secure components of that application to function maliciously. So, for example, an attacker could insert trojans or any other malware in the secure component of the application. Thus, we need to ensure that no secure world software gets tampered with while storing in the flash, and one way to achieve this is by using secure boot. The way secure boot works is by something known as a chain of trust. So, starting from the root device, there is a trust created in the system. Based on this particular mechanism, it becomes very difficult to tamper with. A typical chain of trust looks something like this. We start with a particular component known as the root of the trust. This could be a physically unclonable function, on-chip ROM, or a trusted platform module, or a TPM. So, this is the basic or the root of your trust. So, it is assumed that this is your trusted module. So, this trusted module would then first verify that the bootloader has not been manipulated. So, it will do this by checking that the digital signature of your bootloader has not been tampered with. So, this root of trust at the time of boot first starts to execute and verifies that the bootloader has not been tampered with. So, it would do this by verifying that the signature of that bootloader is correct. So, this could be, for example, an MD5 or a SHA or even more complicated digital signatures to ensure that the bootloader has not been manipulated or not been tampered with. So, if it determines that the bootloader is indeed not tampered, then it would pass on execution to the bootloader and the bootloader would then execute. After the bootloader is nearly completing its execution and would want to boot the secure OS, it would first determine that the signature of the secure OS is correct. This can be verified by checking the footprint or by computing the signature of the secure OS present in the flash and verifying this particular signature with a stored signature. If it is found that signature of the secure operating system does not match the signature which is stored, then the secure OS is not booted. On the other hand, if we find that there is a match, then the bootloader has actually verified that no tampering has occurred on the secure OS and it would permit the secure operating system to boot. Now, the secure operating system can spawn various tasklets, and before spawning any of these tasklets, it would, as we seen before, identify that each of these tasklets have not been tampered with. So, in this way, various tasklets are created only after their signatures are authenticated. In a very similar way, the secure OS initiates the boot of the rich operating system only after validating that the signature of the rich operating system is correct. So, in this way, what we see is, due to the presence of a root of trust, we build a chain of trust. First, we obtain trust in the bootloader, then we obtain trust in the secure OS, and from there the rich OS, tasklets, and so on. Now, if any of these modules are tampered with in the flash, these can be detected by the secure chain of trust. The only assumption that we make is that this root of trust cannot be tampered with. That is the only assumption that we make. Another thing to think about is, if you go back to the block diagram, we see that the monitor is part of the secure world. So, could you think about what is the rationale for having the monitor as part of the secure world? In the next lecture, we will look at the Intel SGX trusted execution environment. Thank you.